Check it out now, y'all.
nanoHUB-U, online instruction.
Welcome back. As you may remember that we had been discussing how biomolecules diffuse around and the time it takes for the biomolecules to land on the sensor surface. And we have discussed that how diffusion fundamentally limits this process. Of course, the nanobiosensors makes the best out of this very bad situation, the diffusion limited situation. The nanostructure itself, through its fractal dimension, allows the diffusion process to allow it to collect more biomolecules on the sensor surface per unit time compared to an old or classical sensor. Now, in the last class, we discussed ways to beat the diffusion limit. And I mentioned two specific approaches. One was to do with throw lots of sensors at the analyte. It is something like putting a lot of policemen on the street to look for the suspect, rather than waiting for the suspect to randomly walk around and give him or herself up in the police station itself. That will take, of course, a very long time. The second approach, that was based on droplet evaporation. As we saw that a droplet can essentially reduce by 1,000,000-fold and thereby concentrate the biomolecule, whatever rare biomolecule we had in the analyte, on the sensor itself. We will discuss a third technique today, and then we'll talk about a technique that you would think that would work very well, but actually doesn't. So those are the two topics that I want to discuss today. I want to begin by talking about diffusion in multiple dimensions and how it allows biomolecules to be captured faster in the target. And you'll see this is actually a very simple idea that we actually often do as we are searching for something. I will then talk about the sensor. If you put it on a flow channel and allow the analyte to come to you, and you may think that actually this will make things better. After all, the molecules are directly coming to you by transport or by drift rather than by diffusion. Wouldn't it make things better? So that is the question we will address, and then finally I will conclude. Consider an analyte volume, and on the bottom we have a spherical sensor. Now these red analytes are immersed in an analyte density ρ3, and we already know that the steady state flux can be calculated by the diffusion, equivalent diffusion coefficient, ρ3 minus ρ0. ρ0 is the surface density on the spherical sensor. Now ρ0 would be small because it will assume that everything that is coming into the sensor are being captured. Kf is infinity. And in that case, we already know the value of CDSS. If you put it N, which is the diffusion equivalent capacitance, and correspondingly there will be 1 over A, which is the radius, and 1 over R. Now R in 3 dimension, after a certain period of time, you may remember that the diffusion fronts are gradually expanding away from the sensor surface, and therefore R would be infinity. R would be 1 over R would be 0 within a very short period of time. We are talking about compared to 1 over A. And therefore, a spherical sensors, as you have already seen, captures particles, which is flux to the spherical sensors, is directly proportional to the analyte density, and the total number of particles captured, well, it increases linearly with time t. This is one value. If you didn't do anything special, then a sphere actually catches this many particles per second on its own. Can we do better? Here is an idea taken from biology. And the idea is something like this. We still have our sensor surface, but instead, in addition, we now insert a nanowire-like structure. Remember, the nanowire itself is not a sensor in this particular configuration, but rather nanowire will catch the particles, funnel it down to the sensor surface. So it's like an antenna. Now, of course, the molecules which get captured can diffuse down a little bit and can be re-emitted back to the solution. Of course, then there's no benefit for the nanosphere sensor. On the other hand, if the molecules are captured within a diffusion length, then before it gets captured, re-released, it is actually captured by the sensor, and in that case, we have gotten a signal. So the question is, of these two, which one would perform better? Now we can easily calculate what the corresponding flux of this thing would be. I3 would be the flux that is coming from the three-dimensional volume to the cylindrical surface. So cylindrical surface is like a collection surface. And then they are getting funneled down like raindrops on a window sill and towards the sensor surface. And of course, in steady state, I3 and I will balance each other, and let's calculate those things to see what type of benefit we might get. Now, I3 would be proportional to the density difference between rho 3, which is the bulk volume, and rho 1, which is the one-dimensional density on the cylindrical nanowire itself. And I1 would be the difference between rho 1 to rho 0. Rho 0 is the density on the spherical sensor. Let's calculate these two fluxes. Now we can easily calculate the first flux. That is because we have previously done the nanowire sensor. Do you remember when the flux came directly to the nanowire sensor? All we had to do was to calculate from 3 dimension to 2 dimension this capacitance, which is essentially a cylindrical capacitance of R divided by A. A is essentially the radius of this cylinder, and LA is the length over which the flux, when the particles once captured, are directly transported to the spherical sensor. LA, of course, is not the physical length of the whole thing, because of course particles which are captured here are re-released, so therefore as if they didn't count or they didn't exist. That's I3. What about I1? I1, we have to think about it a little bit. Think about some particles which are coming in here at a distance x from the sensor surface. Now it is going to diffuse in one dimension from here to this sensor surface, and we'll call that Jx. Of course, the injection could occur at any x, so therefore we will integrate it over, and we'll have to multiply with 2 pi a so that it accounts for the surface of the cylinder itself. Once you evaluate these two quantities, this is the diffusion equivalent capacitance in 1D. Rho 1 minus rho 0 is the density difference between these 2 points, and you integrate it out and you can get an expression for I1. And so once you have calculated I1 by integrating over from 0 to LA, and you already know I3, so therefore we can equate them and find out what the value of I1 is, what the flux to the spherical sensor is. Now, this is relatively simple. We have the known values from the previous slide, C32 and C21 from the previous slide. You equate them, eliminate rho 1, and so therefore I can directly calculate the value for I1. Now here is the trick. If the diffusion in the cylindrical surface is faster than diffusing around in the volume, then D1 is significantly larger than D3. You substitute that approximation, and then it immediately gives you an expression where C21 sort of drops out, because actually this diffusion is so much faster that it is no longer limited by the diffusion of this process. It is essentially just limited by how long it takes for the molecules to swim in 3D and get collected by the nanowire itself. So now once you put this expression for C3 to C, once we put the value for C3 to N, simplify a little bit, and out comes a beautiful result. It says that compared to the spherical sensor alone, when you put this nanowire on top of it, its total amplification, the total number of particles captured, will be amplified by the length, by the capture length, to the radius. And if it turns out to be a factor of 100 bigger, then we will have a factor of 100 amplification in the flux rate. It catches like a cylinder, but it integrates to a point, and hence the amplification. Now, this actually appears to have deep roots in biophysics. This strategy of finding something or diffusing to a target faster than you'd think otherwise possible. For example, you may remember from the second lecture, we discussed about a DNA being a long polymer. Here is my DNA, is a long green polymer, and on one segment of the DNA, let's say there is a target, and this particular protein is looking for that target operator. Now, of course, the protein could search for this place on its own by looking for that target in 3 dimensions, never landing on the sensor itself, so interrogating it point by point. But it turns out there is much better strategy is to first land on the DNA, then slide along, and after a little bit get detached, jump to a different segment of the DNA, and then keep doing this. And so long this diffusion process in 1D along the DNA is faster than diffusion in 3D, it turns out that it finds the target much faster. Sounds complicated? Actually not, because you can see if you lost a child in a city, let's say somewhere here, a city that has subways, then you wouldn't really go around randomly walking in the city looking for the child. It is much easier to look for the child a little bit somewhere, hop on the subway, randomly get off at some other point, look for the child. So this interaction between 3-dimensional search and 1-dimensional fast transport is the essence of the amplification that we got to beat the classical diffusion limit that we have talked about in the previous lectures. That's it. 3 techniques I told you about. There are others, but for the time being, I think these 3 approaches will give you an idea about research direction that people are taking. Let's go on to the final topic, and that has to do with how bringing the molecules to the sensor. Assume that you have a sensor, and in this sensor, if it is sitting in a middle of a flow channel, and the fluid is coming from one reservoir and going to the other. The molecules which are in the reservoir, let's say it's very rare, and obviously the fluid will bring the molecules to the sensor surface, and you might think that this would be better, because instead of sitting around like a jellyfish, it is actually the flow is sort of bringing the food to the jellyfish directly. Wouldn't it be better? And wouldn't a nanosensor benefit from it? You might think the answer is yes, but you can immediately, a little bit closer thought immediately would tell you that the answer isn't so obvious. Because after all, when the molecule is coming to its fast, that's true, but the molecule is also going away from it fast. That's also sort of counterbalancing it. Do I win at the end of the day? In order to answer that question, or in the next 3 or 4 slides, I'd like to do a simple calculation with the following idea. Assume that I have rotated the sensor, sort of it's a rectangular cross-sectional sensor, flow channel. I've rotated it sidewise, and so I'm looking at it from the side. The sensor is on the bottom, which was the circular disc here. On the side, this is laying flat like a little rectangle, a quashed rectangle. The fluid flow goes from 0 on one edge of the plate to the other edge of the plate, and there is a parabolic flow profile. And the idea of that gives this enhancement is that instead of this depletion front gradually going away, as would it happen in normal diffusion limited system, this flow will continuously replenish the density here. So the density will essentially, at a distance delta, is called a stagnant layer. The density will stay clamped, and therefore there may be faster diffusion to this system, because if it were not clamped, the diffusion front would move away, and in that case the diffusion slowdown might have caused me trouble. But how big is delta, and how much enhancement do I get? And here is a relatively simple calculation. In order to understand this calculation, let's quickly define a number. It's called the Peclet number. In this case, it is essentially a ratio of if you didn't do anything versus if you did something. This ratio of these two things. If you did something means that if you had a certain flow rate Q, divided by if you just allowed it to diffuse and there was no flow. And the relative enhancement of the flow rate is with respect to the pure diffusion is given by this number. Now, A is the radius of the disk, H is the height, and W is the width of the channel. Now, after some specific calculations are done, your result will be something like this. It will be rho naught AD if the velocity or flow rate was extremely small, then the result is essentially the same as that of a diffusion case. And you can immediately see that. Forget about when the rho P is small, I can drop these two terms. You can see 4 rho naught AD is essentially the diffusion result that we have seen before for a disk sensor. However, if the flow rate is significant, where Q is large, P is large, in that case you can get a significant gain with a cube root of PE. Let me explain how that comes about. In order to understand how that comes about, you can compare two situations. Situation 1, a disk sitting on the bottom of that flow channel. What is the flux that it will catch? By now we are experts in doing this, so we will simply do the CDSS of the disk. You see, there is no 4 pi. 4 pi was there when it was a sphere or hemisphere. Here it's a disk, and you can look it up in any book, the capacitance of a disk in an infinite medium, and then it will be 4 pi rho naught, 1 over A and 1 over R. And the maximum value that this disk can get purely under diffusion will essentially be the diffusion. When the diffusion front is relatively large, I can drop it, and the maximum value would simply given by 4D rho naught A. Let's say that's my value. Would this be significantly better? The answer is yes. The answer is yes, because this R will no longer go to infinity. Now the R will be pegged at the thickness of the stagnant layer. So instead of simply saying A plus R, R setting to infinity, I will simply have A plus delta being the extent of the R. And once you put it in, we'll get a ratio. We'll get a ratio of these two quantities. And the relative enhancement of the flux, if you take the ratio of these two quantities, will simply be A over delta, essentially of that order. So if your A, this relative size, is actually significantly larger than delta, then you have achieved something, because there will be a significant enhancement of flux capture. Let's calculate very quickly. These are relatively simple calculations. We want to calculate what the value of A and delta is. My goal is, I already know A, the size of my sensor. Delta is what we are after. If the velocity profile is parabolic, then it's given by y, 1 minus y, that type of relationship, normalized to h. H is the height of the channel. And then I can calculate the average velocity, u over 6. And the average velocity must be equal to the flow rate. Q is the total flow rate, volume, and WH is the cross-sectional area of the sensor. I can equate these two to find the expression for U. And once I know U, I can also calculate the value of the change in the velocity or at the bottom point at y equals 0. And if I calculate that, we'll get an expression for Q. So I want to know what the velocity at the top of this stagnant layer is. How do I do that? If I know the rate of change of velocity, I can multiply with delta. And once I calculate it, I will get an expression that relates the flow rate to the velocity and other geometrical factors. Then you have to make a spatial argument. And the argument is the following. That the time it takes for a molecule to go from one side of the sensor after arriving it, before it leaves the sensor and goes away forever, versus the time it takes to diffuse down and get captured by the sensor surface, these two times must be equal. It's only then there will be a capture. Because if the diffusion time takes too long to get to the sensor surface, it will simply disappear forever and it will never be captured. So therefore, that argument simply is reflected by this. If delta is the distance, then the diffusion time is delta square over 2d, and the transport time, tau c, is the size of the sensor divided by the velocity of the fluid. And velocity of the fluid I already know. I put it in, solve for delta, and there is my expression for delta over A, and which goes as the Peclet number to the cube root. So to wrap this discussion up, all you have to do now is to put this expression in here. Imax I already know from the previous calculation. So once I put it in, then I will get an expression that has the flux in terms of the flow parameters. And you can take a log and you can see if your diffusion coefficient is faster, you have larger flux. If you have higher flow rate, larger flux, smaller cross-sectional area, obviously larger flux, and so on and so forth. But the relative improvement is what we are after. In a biosensor, does the flow help or not? Once we have the expression, we can answer this question. And there would be a big surprise for us. So let's see what we mean by that. Let's say I look at the total flux and the volumetric flow rate, which is Q. I plot it as a function of volumetric flow rate. The diffusion coefficient is 150, and let's say we are thinking about 1 femtomolar, very rare analyte density, very low analyte density. If you evaluate the previous expression that we just derived, it will say that if you have a sphere of 100 micron, then you get a 10-fold increase in the capture rate by flow. Tremendous. That's significant. But as you go to nanoscale, what you begin to see is that as your radius is going from 100 to 1 micron, right? Many of the nanoscale sensors are of that order. The relative gain, even at very high flow velocity, is inconsequential, very, very small. What's going on here? In fact, you will see that this happens almost in every place. And the reason is, and I will explain that a little bit later, is this delta relative to A. You see these two things. For nanoscale sensors, A is very small. So in order to get considerable enhancement, you have to make delta also very, very small in comparison. That means impractically high velocity. And therefore, you do not get as much enhancement in the practical case. You could plot the relative enhancement to check it out. how significant the gains are, and the relative enhancement is for 1 micron, as you can see, is essentially negligible. Yes, for larger sensors, significant gain. For smaller sensors, the blue line, not very much at all. So if you put, for example, a cylindrical nanowire sensors in a flow channel, you'd see that as you go from 10 micron to 1 micron down to 1 nanometer, the gain is very small. And therefore, the main conclusion that I want to draw from this analysis is that the large-scale sensors, yes, flow helps a lot, but for small nanoscale sensors, putting it in fluid channel to the 0th order doesn't give you very much. Let me conclude then. The first topic today I discussed was this dimensional modification, allowing from 3D capture it in a cylinder, let it slide down on the cylinder, and then captured by the nanosphere. That gives considerable enhancement. And this is biomimetic in the sense that in biology, DNA proteins detect targets in the DNA exactly the same way. Now, sensors in a flow channel enhances detection. There's no doubt about it because you're bringing things faster. But the counter point is that it also is getting away faster. And so therefore, there is a balance. And what we saw that for larger flow rate, of course, for better detection, larger flow rate. That makes things better because it brings the molecule faster. And you want smaller cross-section. That makes sense, right? Because then the fluid will be hugging the sensor better, and the chances of the biomolecule actually getting caught by the sensor surface is improved. But the point I really wanted to emphasize that these nanobiosensors do not benefit as much as larger classical sensor. So this is another twist of nanobiosensing. Just like the diffusion limit was one type of twist that larger sensors generally don't worry about, similarly, this counterintuitive idea that flow doesn't help nanobiosensors is another aspect that we should be thinking about. Okay, that's it. In the next class, I will continue with this discussion of diffusion limits and how to beat it. And until next time, take care.